Jupiter looks familiar at first glance, a giant world of stripes, storms, and that famous great red spot. But beneath those beautiful clouds lies something far stranger: hidden heat, crushing pressure, lightning-filled depths, metallic hydrogen, and mysteries that even modern missions are still trying to understand. Tonight, we're diving below the surface of the solar system's largest planet to explore what Jupiter may be hiding deep inside its endless atmosphere. Before we begin, please take a moment to like, subscribe, and share this video if you enjoy science documentaries like this one. Thank you so much for being here, and let me know in the comments what time is it where you are and where in the world are you watching from now. Let's begin. Jupiter first presents itself as a world of clarity. Even through modest telescopes, the planet seems to offer a face that can be recognized at once. Alternating bands of pale cream, ochre, rust, and white stretched around a nearly perfect globe, with storms and swirls braided between them, and the great red spot lingering like a wound or a signature in the southern hemisphere. It is one of the few planets that appears richly detailed from so far away, and that familiarity can be deceptive. The striped disk suggests a surface, a topmost layer, something like weather moving across a stable world below. But Jupiter does not possess a surface in the ordinary sense. Its visible face is only the upper expression of a much deeper atmosphere, and even that face is strangely thin compared with the bulk of the planet beneath it. The coloured deck that seems so substantial is only a shallow skin above a descending world of thickening gas, rising pressure, hidden heat, and states of matter that become steadily less like anything found in daily experience. The first secret inside Jupiter's clouds is that the clouds themselves are not the beginning of the planet. They are only the place where vision fails. What appears to be the outer boundary of Jupiter is really a threshold between what sunlight can reveal and what pressure keeps concealed. From a great distance, the planet seems almost decorative, a polished sphere wrapped in orderly bands. Up close, that order becomes restless. The pale zones and darker belts are not painted onto the planet. They are moving regions of atmosphere, shaped by vast jet streams that circle the globe at extraordinary speed. In some latitudes, gases rise and cool, building brighter cloud tops. In others, gases sink and warm, thinning the upper cloud deck and exposing darker material below. The result is not a still pattern, but a continuous act of overturning, a deep atmospheric circulation written into colour. Even the boundary between one band and the next is seldom calm. Where belts and zones meet, the atmosphere shears, curls, and folds into turbulence. Ovals appear and fade, white plumes rise, dark filaments are stretched into long loops, storms merge, separate, or are drawn into larger systems. The famous striped face of Jupiter is less like a painted shell than a map of motion, and every visible feature carries some hint of activity hidden underneath. The clouds themselves are not made of water in the familiar terrestrial sense, at least not in their uppermost visible forms. Near the tops of the cloud deck, ammonia freezes into crystals, forming bright layers that scatter sunlight efficiently and help give Jupiter much of its pale appearance. Deeper down, other cloud layers are thought to form from compounds such as ammonium hydrosulfide and water, stacked beneath one another as temperature and pressure change with depth. This vertical arrangement matters because the Jupiter seen in visible light is only the uppermost accessible part of a layered system. A person hovering high above the planet would not be looking down on a solid world hidden just beneath the haze. Instead, there would be layer after layer of atmosphere extending downward into darker and denser regions, with no sharp line where sky ends and planet begins. That gradual descent is one of the most difficult ideas to hold about Jupiter. Rocky worlds teach the eye to expect a boundary. Gas giants remove it. On Jupiter, depth is not marked by ground but by transformation. The colours of Jupiter deepen the illusion because they make the cloud deck appear even more material than it is. The creams, tans, reds, and browns seem almost mineral, as though the planet was streaked with sediment or iron-rich dust. Yet these tones are likely produced by chemistry unfolding in the atmosphere itself. Material rising from below is thought to bring compounds upward into regions where sunlight, especially ultraviolet light, can alter them. In that changed state, these compounds become colour-bearing agents, often called chromophores, tinting the clouds with the muted reds and browns that make Jupiter so distinctive. The exact recipe remains uncertain, and that uncertainty is important. It means that even the visible hues of Jupiter, so often reproduced in images and so instantly recognizable, are still not fully understood. The planet's appearance is familiar, but the mechanism behind that appearance is still partly hidden. What seems obvious from afar becomes more elusive with study. This pattern repeats again and again in Jupiter science. The more clearly the planet is seen, the more it resists simple interpretation. The thinness of the visible cloud layer only sharpens that sense of concealment, compared with Jupiter's enormous radius. The upper deck that catches sunlight is remarkably shallow. The visual face of the largest planet in the solar system is, in structural terms, a skin. Yet this narrow layer determines almost everything first known about Jupiter. For centuries, observation was limited to what could be seen in reflected light: the belts, the zones, the changing storms, the great red spot, and the changing tones of the atmosphere over time. Those visible features reveal that Jupiter rotates rapidly, that its weather is powerful, and that its atmosphere behaves differently at different latitudes. But they also encouraged a subtle misunderstanding. They suggested that the visible cloud tops were the planet itself. Only later did it become possible to understand that these clouds are more like the upper ripples of an ocean, whose deeper body remains mostly inaccessible. This is why Jupiter feels, even now, like a world partly withheld. It is not merely distant, it is optically guarded. Vision stops long before understanding does. The cloud deck is a curtain, but not an inert one. It is constantly renewed from below and altered from above. Internal heat rises through it. Sunlight strikes it. Radiation modifies its chemistry. Winds tear across it. Lightning flashes somewhere deeper down. Great vortices persist for centuries, perhaps feeding on energy drawn from the surrounding circulation. New storms appear first as buried disturbances before revealing themselves higher in the atmosphere. Bright white clouds tower above neighbouring regions, casting shadows that expose differences in altitude. The visible face of Jupiter is therefore not a passive screen, but a sensitive record of deeper processes. It changes because the hidden planet below it is active. That activity is part of what makes Jupiter so compelling. The clouds conceal, but they also betray. They reveal structure without surrendering depth. They show consequence more readily than cause. Another part of the illusion comes from beauty itself. Jupiter is beautiful in a way that invites confidence. The bands are elegantly arranged, the colours balanced, the disk luminous and coherent. Even violent storms appear from far away as graceful spirals or polished ovals. But Jupiter's beauty is not the beauty of calmness. It is the beauty of scale organised by force. The visible atmosphere is under the rule of rapid rotation, immense gravity, internal heat, and chemical cycling on a planetary scale. Jupiter turns faster than any other planet in the solar system, completing a day in only about 10 hours, and that speed helps stretch atmospheric motion into long east-west bands. The result is a world whose weather is not random in appearance but highly structured. Even when turbulent, order and violence coexist there. Stability and unrest occupy the same frame. The visible planet seems balanced, yet that balance is maintained by perpetual motion. In this way, the cloud tops do something more subtle than hide the interior. They teach the wrong lesson about what lies below. They suggest neatness where there is depth, surface where there is gradient, and familiarity where there is strangeness. To descend into Jupiter even in thought is to leave behind the assumptions shaped by land, sea, and sky on smaller worlds. There is no quiet ground waiting beneath the clouds, no continent obscured by weather, no simple answer to what the planet is made of at any single level. Instead, there is a transition downward through thickening atmosphere into an interior that becomes progressively more compressed, more energetic, and more alien. The bands seen from Earth are real, but they are only the first readable signs of a much larger system. That distinction matters because it changes the nature of the mystery. The question is not merely what Jupiter looks like. The question is what kind of world can produce such a face, and what unseen structure gives rise to the visible order spread across those immense clouds. By the end of this first approach, the cloud tops no longer feel like an endpoint. They feel like a limit imposed on sight, a bright and shifting boundary above a planet whose true body begins where ordinary observation fades. The visible bands of Jupiter are often described as stripes, but that word is too passive for what they truly are. They are not markings laid upon the planet. They are moving atmospheric domains, each one shaped by the rise and fall of gas, by temperature differences, by chemistry, and by the great rotational energy of the planet itself. In the brighter zones, material tends to rise upward from below, cooling as it ascends and helping form pale, reflective cloud tops. In the darker belts, material more often descends, warming as it sinks and thinning the upper clouds so that deeper and darker layers become easier to see. This alternating pattern gives Jupiter its familiar appearance, yet the beauty of the bands only partly reflects their importance. What matters more is that they offer one of the clearest ways to read the hidden motion inside the upper atmosphere. They are not decorative features. They are evidence that Jupiter is continuously overturning itself, carrying material upward and downward across immense latitudinal corridors. The atmosphere is moving in rings around the planet, but it is also exchanging matter vertically, and the visible bands are where these two kinds of motion leave their mark. That exchange helps explain why Jupiter's colours are concentrated where they are. A band is not only a region of wind, it is also a region where chemistry is being exposed, concealed, altered, and redistributed. When gases rise from deeper levels into higher, colder altitudes, they can condense into clouds and enter environments where sunlight, especially ultraviolet radiation, can change their structure. Compounds that may have been colourless or less visible deeper down can become transformed into substances that tint the atmosphere with browns, reds, creams, and muted oranges. These colour-bearing agents are thought to come from material dredged up from below and then processed in the upper atmosphere. That does not mean the matter is simple or well understood. On the contrary, the exact identity of Jupiter's chromophores remains unsettled. Different models have proposed products involving ammonia, sulfur, phosphorus, hydrocarbons, or combinations altered by sunlight and energetic particles. The details remain uncertain because Jupiter is difficult to sample directly, and remote observation reveals consequence more easily than composition. Still, the general pattern is clear enough to be meaningful. The planet's colour is tied to circulation. Its appearance depends on motion. Without the rising of deeper material and the exposure of that material to radiation, Jupiter's atmosphere would not look the way it does. Colour, in this sense, is not surface paint. It is a record of transport. The brighter zones make this especially clear. Their paleness suggests cleanliness, but it is really a sign of altitude and condensation. High ammonia clouds scatter sunlight effectively and give these regions much of their luminous character. In visible light, they seem calm compared with the belts, yet they are not inactive. Their brightness often marks the places where gases from below have risen high enough to cool and form the upper cloud deck. The zones can therefore be understood as regions where the deeper atmosphere communicates upward, though in a softened and filtered form. What reaches the cloud tops is not the full story of what rose. It is only the portion able to survive the journey into the colder air above. The belts speak differently, because gases there are more likely to descend. The uppermost clouds may be thinner or more broken, allowing the eye to reach visually into somewhat deeper layers. This is part of why the belts often look darker and richer in tone. Descending gas suppresses bright cloud formation, and the atmosphere appears less reflective. But the belts are also places where Jupiter's dynamism becomes easier to see. Here the clouds are more likely to be stretched, folded, and torn into complex structures by neighbouring jets and turbulent eddies. Dark streaks branch out like smoke in water. Small storms emerge and are pulled into larger flows. White plumes burst upward into darker surroundings, briefly puncturing the broader pattern before being drawn into it. The belts often appear more agitated than the zones because they are regions where the atmosphere reveals its shearing complexity more openly. Yet the zones and belts are not isolated from one another. They define each other by contrast, and the boundaries between them may be the most active places of all. There, the atmosphere is forced into strong horizontal differences in speed. One jet stream races eastward, another westward. Where those flows meet, the gas does not simply pass in silence, it becomes unstable. Waves form. Vortices are born. Storm systems feed on the available shear. The long-lived circulation of Jupiter depends on this tension. The visible bands therefore record not only vertical motion and chemistry, but also the way rotation organizes conflict across latitude. This relationship between chemistry and circulation becomes even more striking over time. Jupiter's bands do not remain perfectly fixed in appearance. Their latitudes are comparatively stable, but their widths, colours, and textures can change. Some belts fade dramatically, turning pale and subdued before later returning to darker prominence. Others become more turbulent or more richly coloured. Such changes imply that Jupiter's atmosphere is capable of reorganizing itself on timescales visible even within human observation. A band can become less distinct, not because the planet has become quieter, but because the balance of upwelling, subsidence, cloud formation, and chemistry has shifted. These transformations matter because they show that the visible face of Jupiter is responsive to changes deeper down. The band structure is stable enough to define the planet, yet flexible enough to reveal its variability. That blend of permanence and change is one reason Jupiter remains so compelling. It is patterned, but never fixed. The chemistry of the bands is also inseparable from the problem of depth. The upper cloud deck is only the first accessible level. Beneath it lie warmer layers where different compounds may condense, dissolve, or remain mixed as gases. Far below, the water content becomes more important, and deeper still the atmosphere approaches conditions where the very distinction between weather layer and interior begins to blur. The visible bands therefore represent only the highest readable signature of a deeper circulation that may extend far below the ammonia clouds. This is one of the major questions in Jupiter science: how deep do the belts and zones go? And how fully are the visible patterns connected to the deeper interior? The answer matters because it determines whether Jupiter's stripes are shallow weather or the surface expression of planetary scale flows reaching thousands of kilometers downward. Measurements from spacecraft have suggested that at least some of these atmospheric patterns do extend deeply, though not necessarily without change. That result turns the bands from a meteorological curiosity into a clue about structure. They are not merely features of the sky. They may be windows into the planet's bulk behavior. Infrared observations strengthen that interpretation. In visible light, the zones and belts are identified by brightness and colour. In thermal views, they can appear differently, revealing where heat escapes more easily through thinner cloud cover and where thicker clouds trap or mask the radiation coming from below. In these views, some of the darker visible regions become thermally bright, suggesting that they are places where the atmosphere is more transparent to heat rising from Jupiter's interior. This changes how the bands are understood. They are not only differences in cloud colour, they are also differences in vertical structure and energy flow. A belt may look dark in sunlight because its upper clouds are thin, yet that same thinness allows heat from deeper down to escape more readily. Seen this way, Jupiter's bands become a set of moving filters, controlling how the interior announces itself to space. The atmosphere does not simply reflect light, it modulates the outward leakage of heat. The visible face of Jupiter is thus tied to invisible energy rising from the planet's depths. What appears to be a striped globe in daylight is also a thermal world, slowly glowing from within. The chemistry of the bands cannot be separated from that internal heat. Jupiter emits more energy than it receives from the Sun, and that surplus helps drive convection in the atmosphere. Rising material carries not only gases and condensable compounds upward, but also internal energy. The visible cloud deck is therefore suspended above a source of power that does not depend entirely on external illumination. Sunlight matters, especially in modifying the uppermost chemistry, but the engine below is already active. The banded atmosphere exists because Jupiter is not inert. It is a planet still releasing stored and generated energy, and that energy keeps the cloud system alive. The more the bands are studied, the less they seem like a skin, and the more they resemble a dynamic interface between deep physics and visible form. This is why the phrase rising chemistry fits Jupiter so well. The chemistry quite literally rises, brought upward by convection and circulation into levels where clouds form and colours emerge. But the deeper significance is that meaning rises with it. The bands take an unseen process and give it structure, contrast, and pattern. They let the upper atmosphere be read as an index of the invisible. Jupiter's cloud tops do not tell the whole story, yet they are not mute. Their stripes, colours, and instabilities are the first intelligible language of the hidden planet below. And once that is understood, the bands no longer appear as broad decorative belts around a giant world. They appear as active boundaries between deep motion and sunlight, between buried material and visible consequence, between a planet's interior and the fleeting, luminous chemistry at the top of its clouds. South of Jupiter's equator, embedded in the shifting atmosphere like a feature too large to belong to weather alone, the great red spot turns with a strange mixture of permanence and change. At first glance it seems simple enough to describe a giant oval storm, coloured red or rust, rotating counterclockwise in the southern hemisphere and broad enough to swallow Earth with room to spare. Yet almost every part of that description becomes less secure the longer it is examined. It is a storm, but not one that behaves like storms on smaller worlds. It is red, but not always with the same intensity, and the chemistry behind that colour is still not fully settled. It is long-lived, perhaps older than modern science itself, and yet it is not fixed, because its size, shape, and even its place in Jupiter's larger atmospheric balance have changed over time. The Great Red Spot matters not only because it is the most famous feature on Jupiter, but because it reveals how much of the planet's hidden structure can gather into one visible form. It is not merely a stain in the clouds. It is a surviving monument to motion, depth, and energy transfer within the giant planet's atmosphere. Historical observation gives the storm its first layer of mystery. Astronomers have watched some form of large reddish feature on Jupiter since the 17th century, which means the Great Red Spot, or at least a related long-lived circulation, may have persisted across centuries of human observation. That duration alone is difficult to absorb. On Earth, even the strongest storms are temporary. Hurricanes organize, intensify, weaken, and dissipate. Seasonal patterns return, but individual vortices do not hold their identity for generations. Jupiter permits something else. It allows a storm to become almost geographical, as though weather has acquired the persistence of land. Yet even here caution is needed. The Great Red Spot is not immortal in a simple sense. It has been shrinking for a long time, becoming more compact and more circular than in older observations, and its coloration has varied from deep brick red to much paler tones. What has endured is not sameness, but continuity. The storm survives by changing. That distinction matters because it turns the red spot from an atmospheric curiosity into a problem of maintenance. What process keeps such a vortex alive for so long, even as the surrounding planet remains turbulent and variable? Part of the answer lies in Jupiter's banded circulation. The Great Red Spot does not float in isolation. It occupies a latitude where powerful east-west jet streams move on either side of it, helping confine and shape the storm. In a rapidly rotating atmosphere like Jupiter's, these jets divide the globe into long corridors of motion, and large vortices can become trapped between them, once established. Such a vortex may feed on the surrounding shear, drawing energy from the differences in atmospheric flow nearby. The Great Red Spot is therefore not a detached object, but a local concentration of planetary scale dynamics. It survives because Jupiter provides an environment where rotational order and atmospheric instability cooperate rather than cancel. On Earth, continents, oceans, mountains, and surface friction disrupt storms and rob them of coherence. Jupiter offers no such solid interference. Its upper atmosphere is a flowing system wrapped around the whole planet, and the Great Red Spot endures within that flow as a giant eddy that has found an unexpectedly durable niche. Even so, the storm is not an empty whirlpool. Its visible form tells only part of the story. The red spot rises higher in the atmosphere than many of the surrounding clouds, which helps explain why it can look so distinct. Elevated material receives sunlight differently, especially ultraviolet radiation. And that may be one reason the storm's colour is often stronger than the tones around it. Compounds lifted into the higher atmosphere can be broken apart and recombined by radiation, producing colour-bearing substances that accumulate or become more visible in the upper reaches of the storm. This does not solve the chemistry completely. The exact identity of the responsible materials remains uncertain, as it does for many of Jupiter's broader chromophores, but the pattern is suggestive. The Great Red Spot may be red not because it is compositionally separate from the planet, but because it is dynamically positioned to process atmospheric material in a different way. Height becomes chemistry. Circulation becomes colour. The storm's appearance is therefore tied to its structure, and its structure is tied to the deeper behaviour of the atmosphere around it. Infrared observations add another layer to that interpretation. Invisible light. The Great Red Spot appears as a coloured oval lodged within the banded cloud system. In thermal views, it can stand out differently, often appearing darker at certain wavelengths because the cloud structure there blocks or alters the escape of heat from below. This indicates that the storm is not merely a swirl on the surface of the cloud deck. It is a vertically organised system with its own architecture, extending above and below the surrounding layers in ways that affect how radiation moves through it. That vertical organization became even more important with close spacecraft measurements. Rather than being a shallow stain in the topmost clouds, the Great Red Spot appears to extend downward well beneath the visible deck, a reminder that even Jupiter's most iconic feature is not skin deep. The visible oval is only the upper expression of a deeper atmospheric column, one that reaches far below the eye's limit. This matters because it changes the scale of the storm conceptually. The Great Red Spot is not simply broad, it is thick, rooted, and dynamically connected to the interior structure of the atmosphere. What seems from afar like a painted oval is in fact a three-dimensional engine. The deeper story of the red spot is therefore not just about endurance, it is about energy. A storm that persists for centuries must continually resist decay. Turbulence alone cannot explain that persistence. Some source of maintenance must keep the vortex coherent even as it radiates energy, exchanges momentum with neighboring flows, and sheds smaller structures around its edges. One possibility is that the surrounding jet streams and nearby turbulence continuously feed the storm, providing energy through interaction and merger with smaller vortices. Another is that the vertical structure of the atmosphere allows the storm to stabilize itself in ways not possible on terrestrial planets. Jupiter's rapid rotation, strong stratification, and lack of a solid lower boundary all create an environment where large anticyclonic systems can remain organized for very long periods. The Great Red Spot may therefore be best understood not as a storm that has somehow avoided death, but as a storm living within precisely the conditions that allow its survival. Jupiter does not merely host the red spot, it sustains the class of physics that makes such a structure possible. Yet the changes in the storm's size suggest that this support is not unlimited. Over time, the Great Red Spot has contracted significantly compared with older measurements. It remains enormous, but no longer at the scale once recorded. That shrinkage introduces a quieter tension into the story. The storm is ancient, but perhaps not permanent. It may be adjusting toward a new equilibrium, or it may be slowly losing the support that once kept it broader. The same atmosphere that sustains it may also be reshaping it. This gives the red spot a more complex dignity. It is not a timeless mark on Jupiter. It is a long negotiation between persistence and erosion. That negotiation also plays out in the storm's interactions with other vortices. Jupiter produces many ovals and storms, some white, some reddish, some temporary, some more durable. At times, these smaller systems approach, merge, or pass near the red spot, and such encounters can influence its shape and colour. The atmosphere around the storm is therefore never entirely settled. Even the most stable vortex on Jupiter exists within a moving population of disturbances, each one a possible source of reinforcement or disruption. In that sense, the Great Red Spot resembles a deep whirl in a fast river, holding its identity while everything around it changes. It is stable, but only dynamically stable, a form maintained by continual adjustment. This is one reason the red spot remains so scientifically valuable. It is a visible test case for how Jupiter stores and redistributes motion. To understand the storm is to learn something about the atmosphere that supports it, the chemistry it elevates, the heat it overlies, and the deeper layers to which it may be connected. What begins as a famous coloured oval ends as a compressed summary of Jupiter itself. Scale, depth, chemistry, turbulence, and time all meet there. By the time the Great Red Spot is seen in this way, it no longer looks like an isolated marvel. It becomes a threshold feature, one of the places where Jupiter's hidden atmosphere rises into an interpretable shape. Its colour is uncertain, its future unsettled, and its roots deeper than first imagined. That is what gives the storm its lasting force. It is not simply large or old. It is one of the clearest signs that the cloud tops of Jupiter are not the whole planet, but only the place where a deeper circulation briefly becomes visible enough to name. For centuries, Jupiter was known by reflected light alone, which meant that its appearance was shaped almost entirely by what sunlight revealed at the tops of the clouds. The bands, the storms, the drifting ovals, and the great red spot all belong to that illuminated outer layer. But Jupiter is not only a world that reflects light, it is also a world that emits its own. This is where the veil of the cloud deck becomes more than a visual boundary and starts to behave like a filter, invisible light. The upper clouds decide what can be seen by scattering or absorbing sunlight. In infrared, a different Jupiter begins to emerge, because the planet's own heat is trying to escape upward through the atmosphere, and the success or failure of that escape depends on how thick, thin, high, or broken the overlying clouds happen to be. The result is a view that reverses ordinary expectation. Regions that appear bright and pale in visible light can become dark in thermal images, while darker belts and thinner cloud regions can glow more strongly. The atmosphere that once seemed like a painted surface becomes legible as an energy system. This matters because infrared observations do not merely add another way of looking at Jupiter. They reveal that the planet is powered from within, and that its clouds are part of a long upward journey made by heat generated and stored deep below. One of the most striking facts about Jupiter is that it emits more energy than it receives from the Sun. This does not mean the planet is hot in the way a star is hot, nor does it mean it shines visibly by its own light, but it does mean that Jupiter is not in simple radiative balance with sunlight alone. The planet is still giving off internal energy, the lingering result of its formation, its slow contraction under gravity, and the enormous pressures acting throughout its interior. As Jupiter gradually settles and contracts over immense timescales, gravitational energy is converted into heat. That heat does not remain trapped forever. It moves outward through the planet, first through deeper layers where the distinction between atmosphere and interior becomes less clear, then upward toward the visible cloud regions where it begins to leak into space. Seen from far away, Jupiter's beauty seems to come from sunlight on clouds. Seen thermally, the planet becomes something more intimate and more powerful, a giant body quietly glowing from within, carrying its buried energy upward through a turbulent atmosphere. Infrared images make this visible in a direct way. At certain wavelengths, the cloud deck becomes partly transparent to thermal radiation, and the regions where heat escapes more efficiently stand out against those where thicker upper clouds block or mask it. In these views, the lower altitude reddish belts can appear bright, because the clouds above them are thinner and allow deeper warmth to emerge. By contrast, bright white regions in visible light often become darker in thermal imagery because their high, thick ammonia clouds act like blankets, limiting the escape of infrared radiation from below. The Great Red Spot can also appear dark at some infrared wavelengths, not because it lacks energy, but because its elevated cloud structure obstructs the outgoing heat more effectively than neighbouring areas. This reversal is scientifically important because it turns appearance into structure. It shows that visible brightness is not the same as thermal openness. A bright cloud in sunlight may be a thermal lid. A dark region in visible light may be a window. Once that is understood, Jupiter's banded atmosphere no longer looks like a flat arrangement of colours. It becomes a layered landscape of leakage and concealment, where the interior announces itself unevenly through whatever paths the atmosphere permits. The phrase heat beneath the veil is therefore more than a metaphor. Jupiter's upper clouds quite literally veil a warmer world below, and the structure of the veil determines how that warmth appears. Infrared observations also make it possible to detect atmospheric disturbances before they become obvious in ordinary light, Storms can begin below the visible cloud tops, carrying excess heat upward from deeper regions. In thermal images, these warmer disturbances may stand out against the surrounding atmosphere, even when visible light still shows little more than a smooth cloud field. This gives infrared a special value. It does not merely confirm what the eye already suspects. It can reveal the early stages of activity still hidden under the upper deck. In this sense, thermal imaging is not just another portrait of Jupiter. It is a method of listening for motion below the clouds before that motion fully declares itself at the surface of vision. That ability changes the narrative of Jupiter's weather. The visible atmosphere becomes less like a complete weather map and more like the final stage of processes that begin out of sight. What reaches the cloud tops has often already been underway for some time, and the thermal signal is the first clue that the hidden system is stirring. This connection between infrared brightness and cloud thickness also helps clarify the vertical structure of Jupiter's atmosphere. Different wavelengths can probe different depths, because gases and clouds absorb and emit radiation in different ways. At some wavelengths, the upper ammonia clouds dominate the image. At others, hydrogen, methane, or ammonia absorption reshapes what can be seen. At still others, the view becomes more directly tied to temperature. This means Jupiter cannot be represented fully by any single image. Every wavelength selects a different conversation with the atmosphere. Visible light emphasizes reflected sunlight and upper cloud color. Thermal infrared emphasizes heat escaping upward. Spectral bands tied to particular molecules can reveal where those molecules are more or less abundant, or where clouds rise high enough to stand above absorbing layers. Together, these views show that Jupiter's cloud deck is not a single sheet, but a tiered and chemically diverse medium, one that both expresses and controls the movement of energy from the interior. The atmosphere is not simply sitting above the heat, it is actively processing it. The poles offer some of the most dramatic examples of this hidden thermal world. In visible light, Jupiter is usually imagined as a planet of broad horizontal bands, but infrared views of the polar regions reveal something quite different. Clustered cyclones arranged around central vortices, especially at the north and south poles, where great storm systems occupy a geometry unlike anything seen in the equatorial belts. These polar cyclones are easier to interpret thermally, because infrared observations cut through some of the visual confusion caused by haze and shadow. Their structure becomes more legible when seen as temperature and altitude differences rather than as sunlight scattered from cloud tops. In such images, lower and warmer regions can stand out against colder, higher cloud structures, giving the storms a three-dimensional presence that visible light alone cannot fully convey. The lesson is important. Jupiter does not merely hide depth beneath its clouds, it organizes that depth differently in different regions of the planet. The familiar striped face is only one atmospheric regime. Near the poles, the hidden heat and atmospheric structure produce a very different architecture of motion. Infrared does not only reveal the interior's power, it reveals that the planet distributes and shapes that power in ways not obvious from ordinary viewing. The internal heat of Jupiter also speaks to the planet's origin. A world that continues to emit excess energy billions of years after formation must still be carrying a deep thermal memory. Jupiter formed in the young solar system under conditions of accumulation, compression, and intense gravitational settling. That formative violence is not over in its consequences. The planet remains a storehouse of that early energy, slowly releasing it through the layered atmosphere above. In that sense, the heat escaping now is ancient. It connects the present weather of Jupiter to the time when the planet was assembling from gas, dust, ice, and rock in the outer solar nebula. Every bright thermal opening in the clouds is therefore not only a local atmospheric feature, it is a point where deep time and present motion meet. The warmth coming through the atmosphere carries a history far older than any storm pattern visible at the top. This gives Jupiter a special kind of continuity. The planet's weather is not detached from its birth, it is partly driven by it. Yet the heat does not rise through a passive medium. As it moves upward, it interacts with layers of changing composition, pressure, condensation, and wind. It fuels convection, helps maintain circulation, and shapes the development of storms. The upward transport of energy is therefore inseparable from the visible complexity of Jupiter's atmosphere. The belts and zones are not simply painted by chemistry. They are sustained in part by a planetary heat engine. The storms are not isolated accidents. They are expressions of a deep system continually moving energy towards space. Even the cloud colours become part of that process, because rising material brings compounds upward into the regions where sunlight can alter them. Internal heat and external radiation work together, each shaping different aspects of what the planet becomes at the top of its atmosphere. Jupiter is therefore not only a solar-lit world and not only a self-warmed one, it is both at once, with the cloud deck serving as the shifting place where these influences meet. By the time infrared has been added to the story, Jupiter's visible face can no longer be mistaken for the whole planet. The bands are still there, the storms still turn, the great red spot still looms, but all of them are now underlit by a deeper truth. Heat is always rising. The atmosphere is always sorting, masking, and releasing it. The clouds do not merely conceal the interior, they regulate the way the interior becomes visible. Seen in that light, the veil over Jupiter is not a wall but a complicated membrane, thin enough to betray the hidden warmth beneath it, thick enough to keep the deeper planet largely unresolved. And that unresolved depth is what makes the infrared Jupiter so compelling. The visible world gives the planet its beauty. The thermal world gives it its weight. Together they show a giant atmosphere suspended above an interior still trying, even now, to make itself known. Pressure is the force that changes Jupiter from a world of weather into a world of transformed matter, high above the planet. The atmosphere still behaves in ways that can be compared, however imperfectly, with familiar meteorology. Gases rise, cool, condense, and circulate. Clouds form and dissolve. Storms rotate. Sunlight strikes the upper haze and reveals structure across the visible disk. But a descent into Jupiter, even in imagination, quickly leaves behind the language of ordinary sky. There is no sharp frontier where the atmosphere gives way to a solid planet beneath. Instead, there is a continuous deepening, a vast downward progression in which the gas grows warmer, denser, and more compressed until the old categories begin to fail. This is one of Jupiter's deepest secrets. The giant planet is not built in layers like stacked shells with clean edges between them. It is built through gradients, through transitions, through the slow overpowering of one physical regime by another. What begins as atmosphere becomes interior without ever encountering ground. The deeper one goes, the less useful it becomes to ask where the sky ends, because Jupiter is a place where the sky itself thickens into the body of the planet. That gradual descent matters because it changes the meaning of hidden depth. On a rocky world, clouds conceal a surface. On Jupiter, clouds conceal a transition. Below the upper ammonia clouds lie warmer levels where different compounds can condense and form deeper cloud decks, including layers associated with ammonium hydrosulfide and water. These are not decorative additions to the atmosphere. They mark the changing thermodynamic conditions of a planet in which temperature and pressure rise together with depth. The deeper cloud layers are harder to observe directly because the upper atmosphere blocks ordinary sight, but their existence helps define the vertical complexity of Jupiter. The visible bands at the top are only the first trace of a column that continues downward into regions where the familiar sky has already become something heavier, darker, and more difficult to separate into weather and world. In these lower levels, convection still matters. Heat continues to rise from within the planet, and the atmosphere remains in motion. But the motion occurs under conditions increasingly remote from anything terrestrial. Pressure rises relentlessly. Gas molecules are forced closer together. Collisions become more frequent. The atmosphere becomes less transparent, less airy, less like an open medium, and more like a compressed body under strain. The old intuition that gases are light and diffuse begins to break down. On Jupiter, gas under enough pressure can become dense enough to behave in ways that seem almost liquid-like, not because it suddenly turns into a familiar fluid at a neat boundary, but because compression overwhelms the spaciousness usually associated with a gas. This is why a descent into Jupiter is not best imagined as falling through empty sky toward a hidden floor. It is better imagined as entering a medium that resists more and more, a medium whose nature is being rewritten by the sheer weight above it. The weight is immense because Jupiter is immense. All of the atmosphere higher up, all of the cloud layers, all of the overlying gas, pressed downward together. Each deeper level supports the burden of everything above. That accumulated force is what makes Jupiter such a revealing place in planetary science. It allows common substances, especially hydrogen, to enter conditions that cannot be sustained naturally on smaller worlds. Hydrogen is the most abundant element in Jupiter by far, joined chiefly by helium with smaller amounts of other compounds mixed through the atmosphere. Near the cloud tops, hydrogen behaves as a gas in the familiar broad sense. Deeper down, under mounting compression, that same hydrogen begins to occupy a different physical reality. Long before reaching the most exotic states, the atmosphere already becomes a place where pressure is the dominant sculptor. The chemistry of the upper clouds still matters, but pressure increasingly determines what kind of world Jupiter is becoming. This deepening also complicates the idea of location. On Earth, altitude can be described against a firm surface. On Jupiter, depth is more abstract. It is measured not only by distance downward, but by pressure level, temperature, and changing material behavior. To speak of going deeper is to speak of entering new conditions rather than approaching a fixed landmark. Spacecraft sense this distinction clearly. Instruments can probe certain pressure levels, detect microwave signals emerging from beneath visible clouds, or infer composition from gravity and magnetic measurements, but they do not descend toward a known floor. They read a world whose interior must be reconstructed from how matter behaves under compression. The hidden Jupiter is therefore not merely unseen, it is inferred through physics. That is part of what gives the planet its strange dignity. The most important transitions inside it cannot be photographed directly. They must be understood through their consequences. Water offers one example of this buried complexity. In the upper atmosphere, water is not the dominant visible cloud former, which is one reason Jupiter's cloud tops differ so much from terrestrial weather. Yet deeper down, where temperatures and pressures are greater, water becomes far more important. Water clouds are thought to exist well below the upper ammonia layers, and these deeper regions may be tied to powerful convection, lightning, and storm generation. Water is significant not only because it helps drive weather, but because its abundance offers clues to Jupiter's formation history. How much water the planet contains, and how that water is distributed with depth, may help reveal how Jupiter assembled in the early solar system. Yet water is difficult to measure precisely because it is largely hidden below the visible atmosphere. This is one of the recurring patterns in Jupiter science. The substances most crucial to explaining the planet often lie below the level where sunlight can help. Deeper truth requires deeper inference. The problem grows more severe with every increase in pressure. At sufficient depth, the distinction between atmospheric circulation and planetary interior begins to blur. Jupiter's winds may extend far below the cloud tops, but not forever. At some stage, the increasing density of the medium and the changing conductivity of matter alter the character of motion itself. This is where descent becomes conceptually difficult. A person used to thinking in terms of atmosphere above and interior below must adapt to a world where those categories overlap. Jupiter's outer body is not a shell resting on a different kind of planet. It is the outer part of the planet, gradually transformed by compression into deeper and stranger forms. The atmosphere is not separate from the interior, it is the beginning of it. That insight removes one of the most persistent illusions created by the cloud deck. The visible top of Jupiter is not the top of something solid. It is the brightest accessible part of a descending continuum. Pressure also has a quiet narrative power on Jupiter, because it explains how the planet can hide so much without using walls. There are no mountain barriers, no crustal plates sealing off an underworld, no ocean surface dividing air from fluid. Secrecy comes instead from gradual opacity and increasing force. Light fails before matter changes completely. Vision is lost while the transition is still underway. This is why Jupiter has often felt more unknowable than rocky planets, despite being large and visually prominent. The hidden regions are not merely underground. They are below the point where the atmosphere becomes unreadable. And once unreadability begins, pressure keeps altering the material further, leading toward forms of hydrogen and helium whose behavior must be modeled rather than witnessed. It is a concealment produced by physics rather than by distance alone. Even the notion of survival becomes less meaningful in such a descent. There is no stable path downward through Jupiter in the ordinary sense. Pressure rises, temperature rises, and the medium thickens until any object entering from above would be crushed, heated, and ultimately assimilated into the planet. The atmosphere is not empty space to be traversed. It is substance, and at depth it becomes overwhelmingly so. This gives Jupiter's clouds a more profound role. They are not simply weather floating over hidden depths. They are the luminous upper threshold of a domain that becomes steadily less hospitable to ordinary matter and ordinary intuition. Below them lies not a buried landscape, but a transformation zone stretching downward through immense pressure into one of the most alien interiors in the solar system. By the time this is understood, the visible face of Jupiter has changed again. The belts and storms remain real, but they now hover above a descending world in which the meaning of gas, cloud, weather, and planet all begin to merge. That broader setting matters because it prepares the next and harder realization. Pressure inside Jupiter does not only compress matter. Deep enough, it changes what matter is allowed to become, pushing common hydrogen beyond its familiar identity and into a state so strange that it begins to resemble liquid metal more than gas at all. Hydrogen is the simplest element in the universe, and inside Jupiter it becomes one of the strangest. Near the top of the atmosphere, hydrogen behaves in the expected way, as a gas mixed chiefly with helium and carried upward and downward through cloud layers, jet streams, and storms. It is easy to imagine this upper hydrogen as part of the familiar language of planets, a light component of a giant atmosphere spread over a world too large to grasp all at once. But Jupiter forces hydrogen far beyond that familiar role. As depth increases and pressure climbs to extremes impossible at the surface of Earth, the element that usually seems thin, diffuse, and chemically modest is driven into a new state. The deeper atmosphere ceases to be an airy sky and becomes a place where hydrogen is packed so tightly that its electrons are no longer bound in the same ordinary way. Under these conditions, hydrogen is thought to turn metallic. This is one of the most remarkable ideas in planetary science. because it means that a substance normally associated with gas flames, stars, and laboratory simplicity may, inside Jupiter, behave like an electrically conducting liquid metal. No iron is required for this transformation. No ordinary metallurgy is involved. Pressure alone reorganizes the element. That transition is one of the central secrets hidden beneath Jupiter's clouds, because it connects the visible atmosphere above to the invisible machinery that helps make the whole planet what it is. The phrase metallic hydrogen can sound almost poetic at first, as though it belongs more naturally to speculation than to physics. Yet the idea emerges from a straightforward question. What happens when hydrogen is compressed so intensely that the spacing between its atoms is forced toward a regime where ordinary molecular structure can no longer survive? At low pressures, hydrogen generally exists as paired atoms, forming molecules that behave as a gas under everyday conditions. But inside Jupiter, the burden of the overlying planet becomes so great that these simple molecules are squeezed beyond their usual identity. Temperature is also rising with depth, and together heat and pressure begin to alter the structure of matter itself. Somewhere within Jupiter, the molecular hydrogen of the outer regions is thought to give way to a deeper layer in which hydrogen behaves as an electrically conductive fluid. This does not necessarily occur across a single, clean boundary, and that detail matters. Jupiter rarely offers sharp divisions when a gradient will do. The change may unfold across a broad transition region, with hydrogen becoming progressively more compressed, dissociated, and conductive as the descent continues. Even so, the overall implication is extraordinary. Beneath the clouds and weather, Jupiter may contain an immense global ocean not of water, but of metallic hydrogen, a region where common matter enters one of its least intuitive planetary forms. The word ocean is helpful only to a point. It suggests continuity and fluidity, both of which are useful, but it also risks sounding too gentle. A terrestrial ocean is cool by comparison, chemically familiar, and limited by a surface. The metallic region inside Jupiter would be nothing of the kind. It would exist under pressures so severe that the concept of ordinary liquid behavior must be handled carefully. It is better understood as a deep fluid domain in which hydrogen conducts electricity because the electrons can move more freely through the compressed material. In that sense, it resembles a metal, not because it looks like one in sunlight, but because it supports electrical currents in a metallic way. That distinction matters because it is the key to one of Jupiter's greatest powers. A moving, electrically conducting fluid inside a rapidly rotating planet is exactly the kind of environment capable of generating a magnetic field of enormous strength. The hidden metallic hydrogen layer is therefore not merely an exotic curiosity. It may be one of the main engines behind Jupiter's magnetism, linking the deep interior to an invisible influence that extends far out into space. Before that consequence is followed outward, the inward logic is worth lingering over. Jupiter is mostly hydrogen and helium, which at first can make the planet seem simple in composition, compared with rocky worlds rich in silicates, metals, and ices. But simplicity of ingredients does not mean simplicity of structure. Under enough pressure, the behavior of even the lightest elements becomes complex. Jupiter demonstrates this with unusual force. A planet dominated by hydrogen does not remain merely gaseous all the way down. Instead, it becomes a place where hydrogen explores physical possibilities that smaller worlds cannot sustain. In this way, Jupiter is not only a giant planet, it is a natural experiment in matter under compression. Its interior asks what the most abundant element in the cosmos becomes when gravity is allowed to keep squeezing. The answer appears to be that hydrogen crosses from a molecular outer domain into a deeper conductive one, and that crossing changes almost everything about how the planet works. It changes the way heat is transported, the way the interior couples to rotation, and the way electrical currents arise. It may also help explain why Jupiter's magnetic field is not only strong, but structured in unexpectedly complex ways. This is one reason the metallic hydrogen layer occupies such an important place in understanding Jupiter. Many of the planet's most dramatic properties point back toward it. The idea of metallic hydrogen also helps resolve a subtle misunderstanding about gas giants. The name can encourage the thought that Jupiter is loosely assembled, a swollen body of gas lacking the density or coherence associated with more substantial planets. But the deeper interior makes that picture impossible. Jupiter is not a frail envelope around emptiness. It is a massive, increasingly dense world whose outer atmosphere gives way to regions under crushing pressure. The metallic hydrogen layer, if described only briefly, already conveys that changing character. It implies weight, depth, and physical seriousness. It means that below the visible weather lies matter so compressed that the ordinary difference between gas and metal begins to blur. Jupiter is therefore less like a balloon and more like a planet whose outer softness hides a powerful internal body. The apparent gentleness of the clouds tells almost nothing about the conditions farther down. Even the transition into metallic hydrogen carries uncertainty, and that uncertainty is part of its scientific value. Researchers can model the pressures and temperatures inside Jupiter, reproduce some related effects in laboratories for very brief moments, and compare those models against spacecraft measurements of gravity and magnetism. But the exact behavior of hydrogen under Jupiter-like conditions remains difficult to pin down completely. The boundaries may not be neat. The conductivity may vary with depth. The interaction with helium may matter in ways still being refined. In some models, helium separates from hydrogen under certain interior conditions, possibly forming droplets that descend deeper into the planet. Such a process would alter both the thermal structure and the composition of the interior over time. This possibility adds another layer of quiet complexity to the metallic region. It may not be compositionally uniform, and the deep behavior of the planet may involve not only compressed hydrogen, but the slow rearrangement of helium within it. Jupiter's inner world is therefore not simply strange, it is active, layered, and evolving even where direct observation cannot reach. The significance of metallic hydrogen becomes even clearer when placed beside the cloud tops above. At the surface of visibility, Jupiter seems dominated by colour, turbulence, and changing weather. Deeper down, beneath those cloud systems, lies a region where chemistry gives way to conductivity, and motion becomes coupled to magnetism. The upper atmosphere and deep interior may appear almost unrelated at first glance, yet they are bound together within one enormous planetary body. Heat rising from below helps drive the circulation above. The distribution of mass in the interior affects the gravity field measured from orbit. The conducting layer helps produce the magnetosphere that shapes auroras and radiation belts far beyond the atmosphere. Jupiter's clouds are therefore not floating atop an unrelated abyss. They belong to a planet whose deeper structure continuously influences what happens above. Metallic hydrogen is part of that hidden continuity. It is one of the reasons the visible Jupiter cannot be understood in isolation from the invisible one. This deep conducting region also gives Jupiter a kind of dignity rare among planets. There is something quietly profound in the idea that beneath its beautiful bands and famous storms lies a domain made not of rock, not of ocean, but of an element driven by gravity into a metallic state. It feels like a reminder that planetary interiors are not merely buried versions of familiar landscapes. They are places where matter obeys the same laws found everywhere else, yet under conditions so extreme that those laws produce forms almost beyond intuition. Jupiter does not invent new physics. It reveals the full range of ordinary physics under extraordinary compression. That is why the metallic hydrogen layer matters so much. It is not a decorative mystery inserted into the planet's story. it is a central transformation, one that marks the point where descent into Jupiter becomes descent into a fundamentally different kind of world. By the time this is understood, the cloud tops feel farther away than ever. Above them lies weather, chemistry, and visible motion. Below them lies the deep conductive body of the planet, where hydrogen itself is remade by pressure into the hidden medium from which Jupiter's greater powers begin to rise. Jupiter's centre is hardest to imagine precisely because it refuses to behave like a centre should. On a rocky planet, the word suggests firmness, a dense core clearly separated from the layers above it, a buried anchor holding the world together. Even when no one can see that interior directly, the picture remains intuitive. Matter settles, heavy material sinks, a compact middle forms. For a long time, Jupiter was often understood in much the same way. Beneath the clouds, beneath the deepening atmosphere, beneath a strange ocean of metallic hydrogen, there would be a core perhaps rocky, perhaps icy, perhaps mixed, but still recognizably central, a dense object at the bottom of the planet's layered descent. That expectation was not unreasonable. Giant planets are thought to have formed in ways that likely involved some early concentration of heavier material, a seed around which hydrogen and helium later gathered in vast amounts. Yet when spacecraft measurements became good enough to test the structure more carefully, Jupiter's centre did not emerge as a neat buried sphere. Instead, it became uncertain in a more interesting way. The deeper question was no longer whether Jupiter had something heavy at the middle. The deeper question was whether that heaviness remained compact at all, or whether the centre had become diffuse, diluted, and spread upward into a broad inner region that no longer deserved to be called a core in the ordinary sense. This is the hidden core question, and it changes the planet profoundly. The most important shift came through gravity. A planet's gravity is not only a measure of its mass, it is also a subtle record of how that mass is distributed within it. If a world rotates quickly, as Jupiter does, and if its interior is arranged in certain ways, then the gravitational field measured by a passing spacecraft will carry small departures from perfect symmetry. Those departures can be read, with enough care, as clues to the hidden arrangement of matter below the visible atmosphere. Juno was built to gather precisely this kind of evidence. As it swept past Jupiter on close polar orbits, it measured the giant planet's gravity with a degree of precision far beyond what had been possible before. Those measurements did not suggest a simple compact centre buried beneath otherwise lighter material. Instead, they pointed toward something more gradual and more blurred. The heavy elements inside Jupiter appear to be spread through a much larger fraction of the interior than a classic sharp core model would predict. In other words, Jupiter may possess a centre enriched in heavier material without having a small, well-defined central object. The middle may be real, but it may not hold its boundaries. This is what people mean when they describe Jupiter as having a fuzzy or diluted core. The phrase sounds informal, but the implication is serious. A diluted core does not mean Jupiter lacks internal structure. It means the structure is not arranged into the clean divisions once expected. Rather than a compact lump of rock and ice sitting cleanly beneath a vast hydrogen envelope, Jupiter may contain a broad inner region where heavy elements are mixed with surrounding material over an enormous depth. The transition from metallic hydrogen above to the more enriched central region below may be extended, not abrupt. Density still increases inward. Heavier material still tends toward the middle, but the segregation is incomplete. The centre shades into the surrounding interior instead of ending cleanly. This matters because it changes how Jupiter is understood to have formed and how it may have evolved over billions of years. A sharply bounded core suggests one kind of history. A diluted interior suggests a more active, more complicated one. One possibility is that Jupiter did form around a more compact core early in the solar system, and later partially erased that structure. Under the extreme pressures and temperatures inside the planet, some of the heavier materials once concentrated at the middle may have dissolved, mixed upward, or been redistributed over time. This idea, often described as core erosion or dilution, fits naturally with the fact that Jupiter is not static. Heat continues to flow outward. Convection stirs the interior. The boundary between outer and inner regions may not be impermeable over geological time. If heavy elements can be gradually mixed into surrounding layers, then the planet's earliest architecture may have softened from within. The present Jupiter would then be a world whose centre remembers a compact beginning only imperfectly, as if the original seed of the planet had spread into the interior that grew around it. Another interpretation is more abrupt and more dramatic. Some models have explored whether Jupiter might once have suffered a collision with a large planetary embryo early in solar system history, an impact powerful enough to disrupt and redistribute material in the deep interior. Such an event could help produce a diluted central region by stirring heavier elements upward and preventing the neat preservation of a compact core. This is an intriguing possibility, because the early solar system was a crowded and violent place, full of growing bodies crossing paths and competing for mass. Still, this explanation remains speculative. The gravity data do not record a specific ancient collision. They record the present distribution of mass. Several histories may be capable of producing it. That uncertainty is worth preserving. Jupiter's centre is not interesting because it proves a single dramatic story. It is interesting because the structure now observed leaves the deeper history open. The planet may have mixed itself gradually, or it may have been reworked by violence, or both processes may have mattered. The interior keeps the evidence, but not in a form that is easy to read. The hidden core question also matters for a quieter reason. It forces a reconsideration of what a planet's centre really is. On smaller worlds, the centre is often treated as a destination, the final layer reached after everything above has been stripped away in thought. But on Jupiter, the middle may be more like a region than an object. It may be defined by enrichment and compression rather than by a discrete boundary. That is a subtle but important change. It means the planet is not simply layered like an onion with a tidy kernel at the centre. It is a world in which gradients matter more than edges. This is consistent with everything else Jupiter has already suggested. The cloud tops conceal not a solid surface, but a transition. The atmosphere deepens into the interior without a firm dividing line. Hydrogen becomes metallic through compression across changing conditions rather than at a theatrical threshold. Now even the centre seems to follow the same pattern. Jupiter prefers blurred transitions to sharp declarations. Its interior structure is not lawless, but it is smoother and more distributed than early pictures allowed. The fuzziness of the core also affects the planet's thermal story. The way heat moves outward from deep inside Jupiter depends on composition, layering, and the efficiency of mixing. If heavier elements are spread through a wide inner region, that may alter convection, change the thermal gradient, and influence how quickly different parts of the interior transport energy. This means the core question is not isolated from the atmosphere above. A diluted interior could help shape the long-term cooling of the planet, and therefore contribute indirectly to the energy still rising toward the cloud tops today. Jupiter's visible weather, deep metallic hydrogen region, magnetic field, and central structure are not separate mysteries stacked one beneath another. They are coupled parts of one planetary body, changed the distribution of heavy material at the centre, and the consequences may extend upward through the whole system. There is also a philosophical shift hidden inside this scientific one. For generations, planets were often imagined as simpler inward than outward. Their surfaces and atmospheres looked complicated, while their interiors seemed likely to reduce into increasingly basic layers. Jupiter reverses that expectation. The closer thought moves toward the center, the less tidy the picture becomes. The cloud tops are restless, but visible. The deep atmosphere is concealed, but conceptually understandable. The metallic hydrogen region is exotic, but physically coherent. The center, by contrast, returns uncertainty to the story. It is not empty uncertainty or ignorance for its own sake. It is a productive uncertainty shaped by real measurements, one in which competing models must answer to gravity, rotation, composition, and planetary history. But it is uncertainty nonetheless. The giant planet still withholds the one feature that human intuition most wants a clearly defined middle. That withholding is part of Jupiter's character. The world does not simply hide its interior behind clouds, it hides the very boundaries by which interior would normally be described. In this light, the hidden core question becomes more than a technical issue in planetary modelling. It becomes a final refinement of the lesson Jupiter has been teaching all along. The visible planet looks like it has a surface, but it does not. The deep atmosphere looks like it should give way to simple layers, but it changes gradually instead. The centre looks like it should be compact and final, but it may be broad and mixed. Jupiter is a planet of enormous mass, yet it resists hard edges. That resistance does not make it vague. It makes it subtle. The gravity data do not dissolve the centre into nothing. They reveal a centre whose meaning is more distributed than expected, a buried region where heavy elements may be real and influential without being neatly confined. By the end of that realization, Jupiter's middle no longer feels like the missing piece of an ordinary planet. It feels like the deepest expression of the planet's nature, immense, compressed, structured, and still unwilling to reduce itself to a simple hidden core. Long before any spacecraft measured it directly, Jupiter had already declared the presence of something immense and invisible around it. The clue was not a line on a graph at first, but a consequence auroras blazing at the poles, charged particles trapped and accelerated through a vast surrounding region, and an environment so harsh with radiation that any machine entering it would need to be built like a survivor rather than an observer. Such effects do not belong to clouds alone. They point back toward a hidden engine, something inside the planet capable of generating a magnetic field far stronger than that of Earth, and large enough to shape space far beyond the visible disk. This is where the secrets inside Jupiter's clouds begin to reach outward. The atmosphere above may be the most obvious sign of the planet's activity, but the magnetic field reveals a deeper level of organization, one tied not to color or weather, but to the movement of electrically conducting matter within the interior. A magnetic field of this scale is not an ornament around the planet. It is a message from below. It says that something deep inside Jupiter is in motion, that the hidden layers are not only compressed but dynamically alive, and that the consequences of that interior motion extend millions of kilometers into space. On Earth, the magnetic field arises through the movement of conducting material in the outer core, helped by the planet's rotation. Jupiter appears to follow the same broad physical principle, but on a vastly different scale and with very different ingredients. The conducting region inside Jupiter is thought to be associated chiefly with its deep layer of metallic hydrogen, where compression has forced the most abundant element in the universe into a state capable of carrying electrical currents. That conducting fluid does not sit still. Jupiter rotates rapidly, completing a day in only about 10 hours, and that speed helps organize motion within the interior. Convection, driven by internal heat rising outward, stirs the conducting layer. Rotation shapes that motion into patterns capable of sustaining a dynamo, a self-maintaining magnetic generator produced by moving electrical charges. The result is a magnetic field of extraordinary strength, the most powerful planetary magnetic field in the solar system. The importance of this cannot be overstated. It means that Jupiter's hidden interior is not merely a repository of mass and pressure. It is an active generator, a buried system in which motion, conductivity, and rotation combine to produce one of the giant planet's defining powers. Yet even that broad picture turns out to be only the beginning. For a long time, it was easy to imagine Jupiter's magnetic field in relatively simple terms immense, dipolar, somewhat like Earth's but scaled up, perhaps tilted differently, perhaps generated in a different material, but still orderly in its large structure. Measurements from spacecraft confirm that Jupiter does indeed possess a strong global field with a dipole component, yet closer study complicated that simplicity. Juno, with its precise magnetometers and repeated close passes over the planet, revealed that the field is not smooth in the way a first approximation might suggest. In some regions it is stronger than expected, in others weaker, and the distribution of magnetic intensity across the planet shows asymmetries in local structure that imply the dynamo source is not behaving in a perfectly uniform or deeply buried fashion. This matters because magnetic fields are one of the few ways the inaccessible interior can announce its architecture. An irregular field suggests an irregular generating region, or at least one whose geometry and dynamics are more intricate than older models allowed. The invisible Jupiter begins to look less like a planet with a single deep magnetic engine, and more like a world in which the dynamo may be operating across regions of varying depth, strength, and composition. One especially intriguing implication is that part of Jupiter's dynamo action may be occurring higher in the planet than once expected. If the field were generated only in a deep, symmetrical conducting shell, some of the magnetic structure might be smoother and more globally average than what Juno has observed. Instead, the field hints that the conducting and convecting layers responsible for its creation may extend into regions where the transition between atmosphere and interior is already becoming complex. In this view, the magnetic field is not just evidence of a hidden metallic ocean far below. It is also a sign that the planet's internal layering, mixing, and conductivity may be arranged in a more subtle way. The deeper atmosphere, the metallic hydrogen region, and the uncertain central structure may all contribute to a dynamo environment that resists overly simple geometry. The magnetic field thus becomes another argument against imagining Jupiter as a sequence of clean shells. Even its invisible power seems to prefer gradients and irregular structure over perfect symmetry. What emerges around the planet is a magnetosphere of staggering scale. A magnetosphere is the region of space dominated by a planet's magnetic field, the place where the flow of charged particles from the Sun is deflected, trapped, accelerated, and reorganized by that field. Jupiter's magnetosphere is so vast that, under the right conditions, it would dwarf the Sun in apparent size if it could be seen directly from Earth. That comparison is not offered for spectacle alone. It captures a real consequence of the dynamo hidden beneath Jupiter's clouds. The field generated inside the planet does not stop at the edge of the atmosphere. It inflates a magnetic domain around Jupiter so immense that the giant planet begins to function not merely as a world but as a system, one with its own radiation environment, plasma structures, auroral processes, and electrodynamic relationships with its moons. The interior is therefore not self-contained. It projects itself into surrounding space. Jupiter's deep conducting layers shape conditions far beyond the cloud tops, turning invisible internal motion into a spatial empire of charged particles and force lines. Among the most beautiful consequences of this are the auroras, at Jupiter's poles, energetic particles guided by magnetic field lines plunge into the upper atmosphere and excite atmospheric gases, producing persistent luminous emissions. These auroras are far more powerful than Earth's, and they are not occasional decorations triggered only by solar activity in the way terrestrial auroras often are. They are enduring features of Jupiter's polar environment, shaped not just by the solar wind but also by the planet's own rapid rotation, its internal plasma circulation, and the contributions of its moons. Infrared and ultraviolet observations have revealed these auroras in extraordinary detail, showing arcs, ovals, and moving bright spots linked to the magnetic coupling between Jupiter and orbiting satellites such as Io. This is where the field becomes not only a planetary feature but a relational one. The hidden engine inside Jupiter reaches outward along magnetic lines and connects the giant planet to objects tens or hundreds of thousands of kilometers away. The interior writes itself across the poles in light. It also writes itself into danger. Jupiter's radiation environment is one of the harshest in the solar system because the magnetic field traps and energizes charged particles so effectively. Electrons and ions become confined within belts and toroidal structures around the planet, especially where material from Io's volcanic eruptions is fed into the magnetospheric system. Spacecraft passing through these regions face severe radiation exposure, enough to damage electronics and shorten mission lifetimes if not carefully planned for. The field that shelters parts of Jupiter's broader domain from the solar wind also creates one of the most unforgiving near-planet environments known. This duality is revealing. Magnetic fields are often imagined as protective, and in many contexts they are. But Jupiter shows that protection and peril can arise from the same source. The deep dynamo creates order in charged space, yet that order includes powerful particle acceleration and confinement. The hidden interior is not gentle simply because it is invisible. Its influence can be measured in shattered electronics, altered trajectories, and human caution. There is another subtle lesson in Jupiter's magnetic field. It gives the planet a second face, one not made of clouds. The visible face is banded, colourful, and storm-rich. The magnetic face is structured in lines, lobes, trapped particles, and auroral footprints. Both faces arise from the same world, but from very different depths. The atmosphere reveals circulation near the top. The magnetosphere reveals conductivity and motion far below. To study Jupiter fully is therefore to understand how these two faces overlap. Internal heat helps drive convection in the atmosphere and the interior alike. Rotation shapes both the jet streams above and the dynamo below. The conducting fluid generates a field that governs radiation and auroras, while the cloud layers above continue to hide the region from which that field is born. The planet remains coherent across these scales. Its visible beauty and invisible force are not separate identities. They are two expressions of one interior logic. By this point, the hidden magnetic giant no longer seems like an abstract planetary property. It feels like the outward reach of everything already buried inside Jupiter pressure, enough to create conductive hydrogen, heat enough to keep matter moving, rotation fast enough to organize that motion, and structure complex enough to produce a field still richer and less symmetric than expected. The clouds remain in place above all of this, luminous and changing, but they are no longer the main boundary of the planet's influence. The true extent of Jupiter lies beyond them, in the magnetic world projected outward from the depths, where the invisible interior continues shaping light, radiation, and charged space long after the visible atmosphere has faded from view. Near Jupiter's poles, the planet stops looking like itself. The familiar image of alternating belts and zones, stretched in long horizontal bands around the equator, gives way to something more concentrated and more surprising, a realm of tightly wound cyclones gathered around the poles in ordered clusters. Each storm vast in its own right, each one rotating beside others in a configuration that at first seemed almost too geometric to belong to weather. This was one of Juno's most startling discoveries, not because the polar regions had been expected to be calm, but because they were expected to remain variations of the same banded planet already known from lower latitudes. Instead, the poles revealed a different atmospheric kingdom altogether. The north and south polar regions are not simply where the stripes bend out of view. They're environments with their own architecture, their own stable arrangements of storms, and their own rules for how Jupiter organizes motion. This matters because it means the giant planet is not governed by one atmospheric logic everywhere. The forces that produce long jets and broad belts across much of the globe do not erase the possibility of a radically different pattern at the top and bottom of the world. Jupiter does not merely wear stripes. It contains multiple atmospheric regimes layered across latitude, and the poles turned out to be among the least expected and most revealing of them. Juno's polar orbit made this discovery possible in a way no earlier mission could match. Earlier spacecraft had offered extraordinary views of Jupiter, but most approaches favoured the lower latitudes, where the planet's banded structure dominates the eye and where the poles remain foreshortened, dim, or partly obscured. Juno changed that geometry. By sweeping over the poles again and again, it looked directly down into regions that had never before been seen in comparable detail. What appeared there was not a single cap of confused turbulence. Instead, there were large cyclonic storms arranged in persistent groups. At the North Pole, a central cyclone is surrounded by several others, forming a pattern that suggests stability rather than chaos. At the South Pole, a similar arrangement appears, though with its own distinct count and geometry. These are not tiny weather cells. Each cyclone is enormous, comparable in size to large terrestrial countries or even greater. Yet they exist in close proximity without quickly merging into one giant vortex or tearing one another apart. That alone makes them remarkable. On Jupiter, where storms are common and atmospheric motion is relentless, the poles host systems that are both crowded and durable, a rare combination that immediately raises harder questions about how such structures can persist. The first temptation is to imagine the polar cyclones as a simple byproduct of fast rotation, but that explanation is not enough on its own. Jupiter rotates rapidly everywhere, and yet the broad equatorial and mid-latitude regions do not organize themselves into these compact circumpolar clusters. Something about the polar environment allows or favors a different balance between confinement, turbulence, and mutual interaction. The cyclones appear to form a packed arrangement in which each storm helps define the space of the others. In some ways, the system resembles a dynamic puzzle, whose pieces remain in place not because they are motionless, but because each one is held by the motion surrounding it. The poles are therefore not merely stormy, they are structured. Their order is not the stillness of a frozen atmosphere, but an order made out of ongoing rotation and close atmospheric negotiation. That distinction is important because it shifts the scientific problem. The question is not only how the storms formed, it is how they remain arranged for so long without collapsing into a simpler pattern. Infrared observations helped make the nature of these polar systems clearer. In visible light, clouds can hide depth behind brightness, and shadows can complicate the reading of altitude and structure. Infrared views change the emphasis. They reveal temperature contrasts, expose lower and warmer regions where heat escapes more readily, and make the three-dimensional nature of the cyclones easier to interpret. In these views, the polar storms appear as deep atmospheric features with warm and cool structure distributed across their bodies, showing that they are not superficial spirals etched on the upper haze. They are vertically organized systems, standing within the atmosphere with depth and relief, This is crucial, because it ties the storms to the same broader truth that has already emerged elsewhere on Jupiter, visible where there is rarely shallow. Just as the Great Red Spot turned out to be more than a stain at the cloud tops, the polar cyclones also seem to reach below the immediately visible atmosphere. Their significance lies not only in their shape, but in the vertical atmosphere they displace and organize. The poles therefore offer another place where Jupiter's hidden depth rises into view. The clustered pattern of the polar storms carries a quiet mechanical beauty. Cyclones on Earth usually belong to transient weather systems shaped by continents, oceans, and seasonal energy contrasts. Jupiter offers no continents and no solid surface for these storms to brush against. Its polar cyclones live in an atmosphere wrapped around a giant rotating sphere, energized from below as well as influenced from above, without terrestrial friction to wear them down in the same way, and with Jupiter's deep heat still feeding atmospheric motion. These storms may be able to maintain themselves through interactions unfamiliar on smaller worlds. Models suggest that the cyclones may remain separated by a balance of fluid forces that keeps them from merging, with each storm's circulation creating a zone of mutual repulsion or stabilized spacing relative to its neighbors. If that picture is correct, then the polar arrays are not accidental gatherings. They are self-maintaining systems, atmospheric arrangements that survive because the conditions at the poles allow them to coexist in a stable ring around a central vortex. The fact that this is even possible reveals how unlike Earth-Jupiter really is. A world already known for its belts and spots turns out to support still another mode of atmospheric order, one that only becomes visible when the viewing angle is finally right. There is also a deeper implication. The poles reveal that Jupiter cannot be reduced to its most famous features. For centuries, the planet was imagined primarily through its equatorial face, because that is the face most readily visible from afar. The Great Red Spot, the belts, the bright zones, the long jet streams, these became the identity of Jupiter. But the polar regions show that the identity was incomplete. The giant planet contains atmospheric provinces as distinct from one another as climates on a continent, though arranged by latitude and depth rather than by land and sea. The poles are not just decorative extremes, they are a correction to the earlier picture. They show that what appears globally dominant from a distance may only describe a portion of the whole. This is one of the reasons planetary exploration matters so deeply. A new angle of approach can turn a familiar world into an unfamiliar one without changing the world at all. Jupiter did not become stranger when Juno arrived. It had always been this strange. Human knowledge simply had not looked in the right way yet. The cyclones also suggest that energy and rotation are being processed differently at high latitudes. The banded regions of Jupiter are governed strongly by east-west jet streams, which organize cloud motion into long zonal flows. Near the poles, those jets lose their dominance, and other structures take over. The atmosphere there appears less interested in stretching turbulence into ribbons, and more willing to gather it into vortical systems. That difference may reflect how the geometry of the planet and the behavior of rotating fluids change toward the poles. It may also reflect the role of deep convection, local stability, or interactions between storms over long periods of time. The full explanation remains incomplete, and that incompleteness is itself revealing. The poles are not merely visually different, they remain dynamically unsettled in understanding. Jupiter's atmospheric science is not finished when its banded face is described. The polar kingdoms continue the work of uncertainty. They ask how many distinct forms a single planetary atmosphere can take under one rotation rate, one internal heat source, and one giant envelope of hydrogen and helium. There is an almost architectural quality to the polar arrangements, but it would be misleading to treat them as fixed structures in the way a crystal is fixed. They are alive with motion. The cyclones rotate, interact, adjust, and maintain themselves through continuous fluid exchange. Their stability is dynamic, not rigid. That gives them a special place in Jupiter's broader story. They are neither fleeting disturbances nor permanent objects. They are long-lived atmospheric institutions, local governments of motion in a realm where no solid boundary exists. The poles become kingdoms not because they are separate from the rest of Jupiter, but because they rule themselves differently. Their order does not resemble the banded order of the lower latitudes. Yet it is no less real. By the time the polar regions are understood this way, the giant planet has changed again. The old Jupiter of stripes and one great storm is still present, but another Jupiter has appeared above and below it, one of clustered cyclones, thermal depth, and unexpected symmetry. The poles do not end the mystery, they rearrange it. They show that beneath the familiar visual identity of Jupiter lies an atmosphere capable of organizing itself in more than one grand design, and that the parts of the planet once least visible may be the parts that most clearly prove how incomplete the earlier picture had been. A lightning flash on Jupiter does not illuminate a landscape, it illuminates depth. For a brief instant, the discharge marks the presence of a storm system buried below the bright upper clouds, a region where water, ammonia, heat, and rising motion have gathered into an atmosphere thick enough and energetic enough to separate charge on a planetary scale. This is what makes lightning on Jupiter so revealing. It is not simply weather in a more violent form. It is evidence that the giant planet's atmosphere contains deep convective engines hidden far beneath the cloud tops normally seen in sunlight. For a long time, Jupiter's visible face encouraged the idea that its weather was mainly a matter of surface bands, shearing winds, and long-lived vortices at or near the upper cloud deck. But once lightning, deep water clouds, and uneven chemical distributions entered the picture, the atmosphere had to be understood differently. It was no longer enough to describe the visible patterns alone. Beneath the bright ammonia clouds lay a thicker and darker meteorology, one driven by internal heat, loaded with volatile compounds and capable of building storms that begin out of sight and only sometimes announce themselves at the top. The hidden atmosphere of Jupiter is therefore not a calm interior supporting a decorative exterior. It is a restless engine of mixing, a world of buried weather whose deepest layers help shape what the eye eventually sees above. Water is central to that deeper story. Near the cloud tops, ammonia dominates the visible appearance because it condenses at high altitudes into bright icy clouds. But farther down, where temperatures are warmer and pressures greater, water becomes much more important. In these deeper levels, water vapor can condense into powerful cloud systems more analogous, in the broad physical sense, to the storm-bearing regions of Earth's atmosphere, though operating under vastly different conditions and scales. This matters because water is not only a substance carried through the atmosphere, it is a source of latent heat. When water vapor condenses, it releases energy, and that released energy can intensify rising motion, strengthen convection, and help drive thunderstorm activity. On Jupiter, where internal heat is already moving upward from below, the presence of water can turn a buoyant disturbance into a much more vigorous convective tower. That makes deep water clouds one of the keys to understanding how the giant planet builds some of its strongest hidden weather. Yet these water-rich regions lie far below ordinary view. Their storms are mostly concealed by the upper layers, which means the visible atmosphere is often the aftermath or uppermost trace of processes whose real power lies deeper down. Lightning gives those hidden regions away. Electrical discharges require strong vertical motion, particle collisions, charge separation, and enough atmospheric depth for storms to develop internal structure. The presence of lightning on Jupiter therefore implies more than turbulence. It implies tall convective systems rising through deep layers where water clouds can form and interact with ammonia and other compounds. Some of the lightning detected by spacecraft appears in places and at depths that suggest storm development far below the familiar upper deck, and some of it has been associated with towering cloud structures that pierce higher into the atmosphere after beginning deep beneath it. This is scientifically important because lightning is one of the few unmistakable signatures of vigorous vertical transport. It is a direct reminder that Jupiter's atmosphere is not merely sliding sideways in beautiful bands. It is also overturning, punching upward, sinking downward, and continuously redistributing heat and material through a column far deeper than the visible clouds alone would suggest, in that sense. Each lightning flash is a brief disclosure. It says that the deeper atmosphere is active now, whether or not the upper clouds yet show the full consequences. Water does not act alone in this hidden weather. Ammonia plays an equally important role, though in a different way. Ammonia is abundant enough in the upper atmosphere to form the bright cloud tops so familiar in visible images, but its deeper distribution turned out to be more puzzling than expected. One of the surprises revealed by close spacecraft measurements was that ammonia is not spread through Jupiter's atmosphere in the neat. Even way older models had often preferred. Instead, its abundance varies with latitude and depth, and some measurements indicate a pronounced concentration near the equatorial region, extending far below the visible cloud tops. This was a significant result, because it implied that Jupiter's atmosphere is not well described as a fully mixed outer envelope in which gases are simply stirred into uniformity. The distribution of ammonia suggests organized transport, with some regions carrying it downward, others lifting it upward, and still others maintaining persistent differences over great depths. The atmosphere therefore behaves less like a simple, well-stirred container and more like a structured circulation system with chemical memory. Material does not only move, it moves along pathways shaped by the dynamics of the planet. That distinction deepens the mystery, because it means composition itself becomes a tracer of hidden motion. Where ammonia is abundant, one kind of transport may dominate. Where it is depleted, another may be at work. The atmosphere becomes legible not just through clouds and heat, but through the uneven placement of the molecules carried within it. This unevenness matters because it changes the scale of the weather problem. On Earth, meteorology is largely concentrated in a relatively thin atmospheric shell above a solid surface. Jupiter's atmosphere, by contrast, extends downward into a huge fraction of the planet's outer body, and the substances within it do not appear to be mixed into bland uniformity. Instead, the atmosphere preserves latitudinal structure, vertical gradients, and localized disturbances that may extend astonishingly deep. This suggests that Jupiter's banded appearance at the top is tied to circulation systems reaching far below the visible deck. The ammonia anomalies are not just chemical curiosities. They are evidence that Jupiter's weather is rooted in a deep atmospheric engine, one in which composition, heat flow, cloud formation, and convection are all entangled. Water clouds may intensify hidden storms. Ammonia may trace the pathways by which gases rise and sink. Internal heat continues to supply energy from below. Rapid rotation stretches and organizes motion by latitude. The visible bands are only the upper signature of this much larger machine. Another reason water and ammonia matter together is that they may interact in ways that help shape storm formation itself. In some conditions, ammonia can dissolve into water droplets, or participate in mixtures that alter the temperatures and pressures at which clouds form. The atmosphere becomes chemically and thermodynamically layered, with different compounds condensing at different heights and influencing one another as rising parcels of gas move upward through the column. This means a deep convective storm on Jupiter is not simply a plume of warm gas. It is a moving chemical system, one that may gather water from below, lift ammonia-rich material upward, form complex cloud structures, release latent heat, and generate lightning before spreading outward into the visible atmosphere. The upper cloud tops, when they brighten or rise into tall white plumes, may therefore be read as the crest of a process that has already passed through several hidden stages. Jupiter's weather is layered not just by height, but by phase changes, by mixtures, and by energy release at different levels. Such layering makes the atmosphere harder to model, but also more revealing. It means the visible beauty of Jupiter's cloud patterns is supported by deep physical complexity rather than by superficial motion alone. Buried storms are especially important because they restore a sense of vertical drama to a planet often described mainly in terms of horizontal bands. Some storms may first appear in infrared as warmer disturbances below the upper clouds, visible because heat is escaping through thinner regions, or because rising convection has altered the local structure of the atmosphere before the eye can detect anything unusual in reflected sunlight. Later, those storms may manifest as bright outbreaks, plumes, or reorganized cloud bands higher up. This sequence shows once again that the cloud tops are not the start of the story. They are where the story becomes visible. The real beginnings may lie much farther down, where water condenses, ammonia is redistributed, and internal heat pushes upward through an atmosphere already under great pressure. Seen this way, Jupiter's visible weather acquires a hidden prehistory. Every bright disturbance may have begun below sight. Every lightning discharge may mark a deeper region of release. Every chemical irregularity may record long-lived circulation that no ordinary image can capture directly. The atmosphere is not only active, it is stratified in revelation, with different processes becoming knowable at different heights. All of this changes the meaning of Jupiter's clouds one last time. At first, they seem like a surface. Then they become a veil over deeper structure. Then they become a membrane regulating heat from within. Now they become the luminous upper boundary of a convective engine, a restless world of mixing in which water, ammonia, and internal energy are constantly rearranging the planet from below. The hidden depths are not motionless, and they are not compositionally bland. They thunder, they convect, they sort molecules by circulation and altitude. They build storms long before those storms can be seen clearly from outside. This does not settle every question about Jupiter's deep weather, and in some ways it sharpens them. How far downward do the convective systems reach? How does water abundance vary across the globe? Why does ammonia remain uneven at depths where simpler models expected stronger mixing? How do buried storms couple to the banded circulation above? These questions remain open because the atmosphere is still revealing itself layer by layer, yet one conclusion is already difficult to escape. Jupiter's atmosphere is not a static envelope painted with weather. It is a deep and chemical engine, constantly moving material, releasing heat, and producing hidden storms whose upward consequences shape the face of the planet. The clouds, seen from afar, remain beautiful, but beneath them the real weather of Jupiter is still climbing. In July of 1994, Jupiter was struck in public. For 6 days, fragment after fragment of Comet Shoemaker-Levy 9 crashed into the giant planet, and for a brief period the clouds that usually conceal so much instead became a screen on which hidden depth could be read by violence. The event was extraordinary not only because it was dramatic, but because it turned Jupiter into an accidental experiment. Under ordinary conditions, the atmosphere reveals itself slowly, through colour, heat, chemistry, and the measured persistence of storms. During the impacts, those gradual methods were joined by something abrupt. Material from space plunged into the atmosphere at immense speed. Energy was dumped into layers not normally disturbed in so conspicuous a way. Plumes rose far above the cloud tops, and dark scars spread across the visible disk, large enough to rival the most famous storms already present there, for a planet that hides so much beneath its upper clouds. The collisions created a rare kind of exposure. They did not peel Jupiter open in any literal sense, and they did not give a simple direct view into the deepest interior, but they did something almost as valuable. They forced the atmosphere to respond, and that response carried information upward from levels usually hidden from ordinary observation. In that moment, destruction became revelation. The comet had already been transformed before the final collision began. Captured by Jupiter's gravity, it had passed close enough to the planet on an earlier approach to be torn apart by tidal forces, stretched into a string of fragments rather than remaining a single intact body. This fragmentation was itself a reminder of Jupiter's power. The planet does not only dominate its moons and shape its magnetosphere, its gravity can physically dismantle smaller visitors before they ever reach the clouds. When the fragments returned on their final plunges, they entered the atmosphere one after another, striking the far side of Jupiter from Earth's perspective before rotation carried the aftermath into view. Spacecraft positioned elsewhere in the solar system saw more of the direct violence, including the immediate fireballs and the towering plumes that followed. But even from Earth, the scars that rotated into sight were unmistakable. Dark blotches spread across the atmosphere, larger than Earth itself in some cases, and they lingered for weeks and months as the atmosphere slowly dispersed them. Jupiter's face had been altered by collision, and for once that altered face was not only a weather pattern born from within, it was a wound from outside. Yet what made the event scientifically important was not only the scale of the marks, it was the sequence of atmospheric consequences that followed the impacts. When the fragments struck, they released staggering amounts of energy, heating the atmosphere and sending debris high above the surrounding cloud tops. That rising material did not consist solely of comet matter. It also included material from Jupiter's own atmosphere, thrust upward from deeper levels by the force of impact. This was crucial. Spectroscopic observations of the aftermath revealed compounds and elements that provided clues to what had been dredged up and how the atmosphere was layered. Sulfur-bearing compounds were detected, along with heavier elements and signs of water in amounts that drew serious attention. These observations did not solve Jupiter's composition in one stroke, but they offered an unusual sample of sorts, not collected by drilling or descent, but by impact-driven excavation. The planet's own response became a temporary probe. The event showed that under sufficient disturbance, Jupiter's atmosphere could carry deeper material into levels where it became measurable from afar. That realization gave the scars a significance beyond spectacle. They were not only marks of collision, they were openings in interpretation. Another lesson came from heat. The impact sites glowed intensely in infrared as the atmosphere responded to sudden compression, heating, and the return of ejected material falling back downward. In normal infrared observations, heat leakage from Jupiter's interior is filtered through cloud structure and atmospheric capacity. During the Shoemaker-Levy impacts, the thermal pattern was violently interrupted. The atmosphere became a place of transient high temperatures, shock propagation, and altered chemistry. This mattered because it demonstrated how responsive Jupiter's hidden layers are to sudden forcing. The giant atmosphere is often described as stable in its large patterns, and in one sense it is. The belts, zones, and major vortices can persist for long periods. But the impacts revealed that stability does not mean passivity. Disturb the atmosphere hard enough and it reacts on a planetary scale. Heat is redistributed, material rises, winds transport scars around the globe. New chemistry appears in measurable forms. The visible surface of Jupiter may be only a cloud deck, but it is coupled to a larger system fully capable of recording catastrophe. The movement of the dark scars also proved valuable. As the impact debris spread and evolved, scientists could track winds and atmospheric circulation in regions not ordinarily marked so distinctly. The scars became tracers, temporary stains moving within Jupiter's larger flow. By watching how they stretched, drifted, and thinned, researchers gained insight into the behavior of the stratosphere and upper atmospheric circulation. This is one of the quieter gifts of impacts. They do not merely add energy, they add contrast. In a world already crowded with storms and bands, an impact scar creates an artificial marker, something the atmosphere must carry. The path of that marker then reveals motion otherwise difficult to isolate. Jupiter's atmosphere, so often hidden by its own complexity, briefly became easier to read because an outsider had written on it in dark debris. The chemistry of the aftermath also sharpened an older question about water. Water had long been expected to matter deeply within Jupiter, especially in the lower atmosphere where it should condense into clouds far below the visible ammonia deck. Yet measuring its abundance directly remained difficult because so much of the relevant region is obscured. The impact observations, by throwing material upward and changing local atmospheric conditions, hinted again that water was present in meaningful quantities. This did not settle the overall distribution of water throughout Jupiter, but it strengthened the sense that some of the most important compositional truths about the planet lie below normal view. In this way, Shoemaker-Levy 9 acted like a rough and violent preview of later scientific efforts, where later missions would use microwave sounding, gravity measurements, and close atmospheric analysis to infer hidden structure. The comet had done so brutally, forcing the atmosphere to expose pieces of itself through trauma. It is difficult to imagine a clearer example of how catastrophe can become data. The impacts also changed how planetary collision itself was understood. The solar system can feel settled when observed over human timescales. Orbits appear regular, planets stable, moons dependable in their paths. But Shoemaker-Levy 9 demonstrated that major impacts are not relics of a remote, chaotic past. They still happen. Jupiter's gravity makes it especially likely to intercept comets and asteroids, and in that sense the planet may serve as both target and shield within the wider architecture of the solar system. There is still debate over how consistently Jupiter protects the inner planets from catastrophic impacts as opposed to sometimes redirecting potential impactors, but the event made one thing impossible to ignore. Large collisions remain part of solar system life. Jupiter's atmosphere bears that reality more often than Earth's, simply because of its size, mass, and position. The scars from Shoemaker-Levy 9 were therefore not merely a local accident. They were a reminder that Jupiter exists within a continuing exchange between planet and debris, a gravitational relationship that shapes both danger and discovery. There is a deeper narrative symmetry here. Throughout the study of Jupiter, hidden processes have usually been inferred from within internal heat rising, metallic hydrogen conducting, storms fed by buried convection, ammonia patterns tracing deep circulation. The Shoemaker-Levy impacts reversed the direction of disclosure. Instead of the inner planet quietly expressing itself upward, the outer solar system struck downward into Jupiter and forced the atmosphere to answer. The result was still the same in one essential respect. The visible cloud tops were not enough. Understanding came from what disturbance revealed beneath them. Even an external blow ended by pointing inward. That is why the scars matter so much in the story of Jupiter's hidden clouds. They show that the giant planet does not need to be calmly observed to yield information. Under rare conditions, it can be shocked into revealing itself. The dark marks eventually faded. Of course. Jupiter's atmosphere absorbed the evidence, stretched it thin, and carried it away into the broader circulation. The planet regained its familiar face, as though the wounds had never been there, but the knowledge remained. The collisions had shown that beneath the beauty of the bands lies an atmosphere capable of recording and redistributing violence on a scale almost beyond human comparison. They had exposed buried chemistry, mapped winds through drifting scars, and reminded science that Jupiter's clouds are not only a veil over internal mystery, but also a meeting place where forces from deep within and far outside can collide. By the time the last visible traces disappeared, the event had already changed the meaning of Jupiter's surface forever. The cloud tops no longer looked merely like weather. They looked like a responsive boundary, one that could be bruised, heated, excavated, and made to speak, if only for a little while, about the deeper planet hidden below. Jupiter now stands in a different light than it did when its bands first seemed enough to define it. The old image of the planet was powerful but incomplete, a giant striped sphere, a red storm, a bright face wrapped in orderly weather. The newer image is harder to hold in one thought because every layer of understanding points downward toward another uncertainty. The cloud tops are no longer a surface but a threshold. The bands are not markings but circulation. The great red spot is not a stain but a deep vortex. Infrared light shows heat rising from within. Pressure turns atmosphere into interior without a clear dividing line. Hydrogen becomes metallic. The center may not be compact. The magnetic field carries the consequences of hidden motion into space. The poles organize themselves into strange crowns of cyclones. Water, ammonia, lightning, and buried storms reveal a deeper weather system still only partly understood. Even collisions from outside can briefly expose regions the eye was never meant to reach directly. By this stage, Jupiter has become something more than the largest planet in the solar system. It has become a lesson in how a world can be visible and concealed at the same time, familiar in outline yet resistant in structure, generous with beauty and careful with explanation. The giant is no longer withholding answers in the sense of silence. It is speaking constantly through clouds, heat, gravity, magnetism, and motion. The difficulty is that each answer arrives as part of a larger question. One of the most important of those questions concerns depth. How far downward do the visible patterns truly extend? Jupiter's belts and zones clearly belong to the upper atmosphere, but measurements have shown that at least some of the great jet systems continue far below the cloud tops. That finding is significant because it means the planet's weather is not confined to a thin shell. Yet the jets do not extend indefinitely. At some depth, the increasing density and conductivity of the interior must change the rules. Somewhere the familiar language of meteorology gives way to the deeper language of rotating fluid physics and magnetic influence. But where that transition occurs, and how gradually it unfolds, remains part of the unfinished interior. The same question returns in another form when water is considered. Water helps build the deep storms, the lightning, the convective towers hidden beneath the upper clouds, and it may preserve clues to Jupiter's birth in the early solar system. Yet even now, water remains difficult to measure with full confidence across the entire planet. Its abundance may vary, its role may shift with latitude and depth, and its deeper cloud systems remain mostly beyond direct sight. This matters because water is not merely a weather ingredient. It is part of the history of formation itself. To know how much water Jupiter carries is to move closer to knowing how the planet assembled, what solids and ices contributed to its making, and how the giant world came to dominate the architecture of the outer solar system. The hidden interior therefore contains not only the planet's present structure but traces of its beginning. The core question remains equally unsettled. Juno's gravity measurements transformed the old expectation of a tidy central mass into something more distributed and more subtle. Jupiter may possess a center enriched in heavier material without containing a sharply bounded core in the traditional sense. If that is true, then the planet's deep history may include dilution, erosion, or large-scale mixing that blurred an earlier structure. Perhaps the original core spread gradually into the surrounding interior under immense pressure and long convective stirring. Perhaps a major collision in the distant past helped disrupt and redistribute the center. Perhaps the truth involves processes not yet fully imagined. What matters most is not which explanation sounds grandest, but that the center of Jupiter has ceased to behave like a simple endpoint. The middle of the planet may be a region of transition rather than a final buried object, and that changes how giant planets are understood more broadly. A center that does not hold itself neatly apart from the world around it is more difficult to picture, but it may be closer to the truth. The magnetic field carries another unfinished thread. It is clear that Jupiter's dynamo is real and immense, driven by conducting matter in motion within the deep interior. It is clear as well that the resulting magnetosphere transforms the space around the planet into one of the most intense charged environments in the solar system. Yet the exact geometry of the dynamo remains unsettled. The field is not as smooth or as globally uniform as once assumed. Its irregularities suggest an internal generator shaped by gradients, asymmetries, and perhaps levels of conductivity extending into regions that complicate the old layered picture. In this way, the magnetic field does not conclude the story of the interior, it sharpens it. The field says that something powerful is happening below, but it also says that the hidden structure producing that power may be more intricate than early models allowed. The poles deepen the unfinished quality further. They show that Jupiter is not one atmosphere repeated everywhere, but a world with multiple forms of order. The clustered cyclones at the poles remain among the most striking signs that the visible identity of the planet had been incomplete for centuries. Yet even after discovery, their full explanation is still emerging. Why these storms remain stably arranged, how deep they reach, how they exchange energy with the rest of the atmosphere, and why the polar regime differs so strongly from the banded lower latitudes remain active problems. Jupiter's atmosphere keeps proving that knowing one grand pattern is not enough to know the whole planet. Every solved feature seems to reveal another that follows different rules. There is a temptation, at this point, to treat Jupiter as an endless catalogue of mysteries, but that would miss something essential. The value of the unfinished interior is not that it preserves obscurity for its own sake. The value is that the unknowns are now shaped by measurement. They are bounded by evidence. Spacecraft have mapped gravity, sampled the magnetic field, sensed microwave emissions from below the clouds, traced auroras, watched the polar storms, recorded lightning, and followed the chemistry of the atmosphere in wavelengths invisible to the eye. Jupiter is still unresolved, but it is no longer vague. The uncertainty has structure. This is one of the quiet achievements of planetary science. A mystery does not become less profound when it gains firmer edges. It becomes more meaningful because the unanswered parts are no longer empty. They are connected to things already known. Jupiter's remaining questions are anchored in real patterns, real measurements, and real contradictions between expectation and observation. The planet is unfinished in understanding, but not untouched by knowledge. That makes its future study feel less like a hunt for surprise and more like a deepening conversation with a world already beginning to answer in its own language. That conversation will continue through improved models, through new observations, through the long analysis of data already gathered, and the arrival of future missions built to ask sharper questions. But even without naming those missions or predicting their exact findings, the direction is already visible. Jupiter will keep being studied not because it is merely large, but because its largeness allows matter, weather, and magnetism to enter regimes unavailable elsewhere nearby. It is a giant laboratory of pressure, motion, and planetary memory. Its clouds are beautiful enough to attract attention, But what lies beneath them keeps attention from fading. The planet refuses to become simple. That refusal is part of its scientific importance. It forces thought to become more patient, more layered, and more willing to accept gradients where it once expected boundaries. In the end, the secrets hidden deep inside Jupiter's clouds are not a single buried answer waiting to be uncovered all at once. They're a chain of linked uncertainties descending through the planet: how deep the winds run, how water and ammonia are distributed, where weather becomes interior, how hydrogen changes under compression, what shape the center truly has, how the dynamo is organized, why the poles behave so differently, and how all these layers fit together inside one rotating giant. Jupiter's unfinished interior is therefore not a failure of understanding. It is the living frontier of understanding, the place where observation has gone far enough to reveal complexity, but not far enough to dissolve it. The cloud tops still shine in sunlight as they always did, but they now hover above a planet that has become much larger in thought than in sight. What remains hidden is not empty darkness. It is structure still coming into focus, depth still resisting final simplification, and a world whose greatest power may lie in how much it continues to reveal without ever surrendering itself completely. What remains, after all the storms and chemistry and hidden pressure, is a quieter impression of Jupiter as a world that is never fully exhausted by its first appearance. Its clouds seem bright and immediate, yet beneath them lies a long descent through motion, heat, compression, and transformation, a descent that keeps turning simple images into deeper questions. The bands become circulation. The storms become structures with roots below sight. The glow of the planet becomes a sign of energy still rising from within. Even the invisible magnetic field becomes a kind of distant handwriting from the interior, written across space in radiation and aurora. Jupiter does not need a solid surface to feel substantial. Its substance is distributed through depth itself, through the gradual thickening of atmosphere into interior, through layers that cannot be separated cleanly, only understood more carefully. That may be part of the reason the planet remains so compelling. It is not simply large. It is layered in a way that keeps familiar language close to its limit. A cloud is never only a cloud there. A storm is never only a storm. Color is chemistry. Heat is memory. And depth is not emptiness, but structure under increasing force. In that sense, Jupiter offers a calm kind of mystery, not because it refuses knowledge, but because each new answer leaves the world more coherent and more profound at the same time. The giant planet remains suspended between what can be seen and what must be inferred, and perhaps that is where much of its power lies. It is a visible world whose deepest truths still arrive indirectly, through light, gravity, motion, and patient interpretation. And so Jupiter endures not merely as a symbol of scale, but as a reminder that some of the most extraordinary places in the solar system are not hidden by distance alone, but by the richness of what lies just beneath the clouds,